Yes, guten Morgen, Germany. Namaskar and good afternoon, friends from India. My name is Tobias Winter from the Indo-German Energy Forum, and I will guide you through the session today. Today, we are talking about large-scale green hydrogen production. The event is jointly organized by the Indo-German Chamber of Commerce, Indo-German Energy Forum, and the German Vdma as our network partner. And certainly, we are also grateful to our media partner, the Fuel Cell India magazine, which just came up. I'd now like to request Mr. Stefan Halusa, Director General of the Indo-German Chamber of Commerce, to kindly give us his welcome remarks.
Yeah, thank you, Tobias. Good morning from Germany, a very good afternoon to India. A welcome to all the panelists and to all the participants to this knowledge session on large-scale green hydrogen production. This is, of course, not our first event on the topic, but while our last events were focusing more on mobile or stationary green hydrogen technology, this time we are going to focus on large-scale green hydrogen production. As we all know, in order to achieve the targets of the Paris Agreement, many countries around the world are developing or have already developed their own hydrogen strategies. And all over the world, large-scale green hydrogen projects are being announced. In Germany alone, if I have the right information, already 68 commercial power-to-gas projects are currently in operation. And by the end of this year, we hope to reach 1 gigawatt of power-to-gas capacity in Germany. The official goal and objective of the government is to reach 5 gigawatt of electrolyser capacity by 2030. German industry, however, estimates that the requirements should be in the magnitude of 20 to 50 gigawatts of power to gas to X plants in Germany until 2030 and 160 gigawatts by 2050. So it is very obvious that Germany will not be able to cover the own requirements for green hydrogen and will therefore have to import large quantities from all over the world. And this is, of course, where India comes into the game and into the picture. For once, because in order to reduce the cost for the production, we just simply need more scale. We need more large scale of these projects. And second, of course, India has also the objective of decarbonizing the economy. And while doing this and implementing projects, there is also the option then to export green hydrogen, in this case to Germany. In order to bring down the cost for the production of green hydrogen, the government is providing significant funding for large-scale projects, including projects in India, if they are developed in partnership with a German company. The draft of the funding guidelines have been shared in and after an event on May 19, I think we had with IGF. And you may remember that those guidelines provide that one of the targets and the objectives is to achieve the decarbonization in Germany, of course, but at the same time and in parallel in the partner countries. So these guidelines are available with the Indo-German Energy Forum and of course at IGCC. And if there are any questions also with regards to the eligibility criteria of specific projects, you can always reach out to the Indo-German Energy Forum or to IGCC. We will be happy to support. And that also then also the German Association, Mechanical Engineering Industry Association, Vdma, will explain more about German companies and involved in green hydrogen production. And of course, I'm equally grateful that two of our member companies with Siemens and ThyssenKrupp have agreed to give us closer insights into their international green hydrogen projects so that we can all get a better understanding about what is also going on globally in order to fill those mentioned Paris targets. And it goes without saying that we at IGCC are committed to support our member companies in achieving their sustainability targets in India. So again, if you have any questions or requests, please contact any of our offices, 6 offices in India or our office in Germany for support and additional information. With this having been said, again, I would like to hand over back to Tobias, and I'm very much looking forward to achieving new insights and learn a lot about those projects and the involved technologies in those large-scale green hydrogen projects. So thank you very much. Dankeschön, and back to you, Tobias.
Thank you very much, Mr. Loser, for your kind and encouraging words. We are now delighted to have Mr. Peter Müller-Baum with us. He is the Managing Director of Germany's Engineers Association, Vdma, Director of the Working Group Power to X for Applications. So he's very much connected to the entire German hydrogen environment, and he'll give us his insights to the international perspective of German hydrogen technology providers, together with Mr. Rajesh Nath, Managing Director of Vdma India. The floor is yours.
Yeah, thank you very much. I'm very pleased to be invited here to present the Vdma and also our activities in particular regarding hydrogen and power to X. I hope you can see my presentation. We start with a very short introduction of Vdma India, then I give you an overview on the Power to X platform of Vdma, and at the end, and I hope that will be the main focus of the presentation, a short impression from our end regarding the options for hydrogen, for green hydrogen in particular, also with regard to the Indian industry. So first of all, I hand over to my colleague from Vdma India in order to show how the Vdma is based in India as well. Mr. Nath, the floor is yours.
Thank you, Mr. Müller-Baum, and good afternoon to all the participants from Germany as well as in India. Hearty welcome to you on behalf of the German Engineering Federation, Vdma. So friends, what is Vdma? We are the Association of the German Machinery and Plant Manufacturers. In fact, Vdma is the largest industrial association, not only in Germany, but you could say in Europe, having approximately 3,350 members, and the turnover of the Vdma members is at 205 billion euros. Of course, the association and members are dependent on exports, and from this almost 79% is exported. Vdma has a rich heritage and culture. It's a 129-year-old association founded in 1892 and headquartered in Germany, in Frankfurt. We are divided into specialized divisions. So we have 39 specialized divisions within the Vdma. And besides the head office in Frankfurt, Vdma is present in the BRIC countries. And in India, India was one of the earliest foreign subsidiaries of Vdma, and besides that, we are present in China. We have an office in Russia as well as in Brazil. Besides our presence in Brussels, as well as in Poland and Austria and Japan. Next slide, please. So coming to our Indian operation, friends, we are headquartered in Kolkata, and besides our operations in Kolkata, we have presence in Mumbai, Bangalore, and Delhi, covering each of the regions. So from the Vdma members, we have around 600 members who are present in India and well established in India in the engineering sector, right across various industrial applications. Next slide. And this is our key people or management team here in India. We have Jimli John heading our Western region office in Mumbai, then Sandeep Roy in Kolkata for the Eastern region, Ajmal in Noida for Northern region, and my colleague Manohar here in Bangalore. So with that, now I would like to give it back to Mr. Peter Müller-Baum for his presentation. Thank you very much, friends.
Thank you very much, and I will continue with a very brief overview on the Power to X activities of Vdma, here with a platform of more than 140 members, established end of 2018, and increasingly new members on a very regular basis. More and more companies are interested in that platform. So if you are interested as well, the slides which I'm going to present now are shared after that meeting, as far as I know. Please don't hesitate to contact us. Actually, we are covering all typical activities which such an association like the Vdma is typically dealing with. Networking and lobbying are the main activities, but we are also organizing congresses, webinars now during the COVID-19 pandemic, of course, and are doing a lot of PR activities. Networking means in that regard that we are covering the entire value chain from the production of green power. Then the main focus of our activities are, of course, the change, the 2x, the process engineering, but we have also a lot of members who are interested in hydrogen or hydrocarbons or other kind of e-fuels in order to use that for whatever kind of process. Lobbying, as I said, is our main focus, in particular in Germany and Europe, because nowadays everybody is talking about hydrogen, but that wasn't the case already 2 or 3 years ago. And actually, regarding the hydrocarbons or other kind of derivatives made of hydrogen, it's not the case yet. There are a lot of things at the political level which could be better from our point of view. So this is, as I said, still one of our main activities. And we have another focus just created last year in order to increase the network dealing with or considering technical questions. We established a technical committee last year, and with that group, we are already part of one of the main research projects funded by the German government. In addition, and this is probably the reason why I'm invited here for that meeting, we are also dealing with a matter of international markets. I will come to that later on when we see which countries, which regions worldwide are mainly interesting for hydrogen production. At the end, public relations, as I said, is also a very important activity for us in order to inform politicians, but also the broader public on hydrogen and power-to-X technologies in principle. And last but not least, we are going to initiate a conference. I hope that will be a face-to-face conference already this autumn, but as you know, it's not 100% clear yet. But we think it's necessary that the community has a platform to meet each other and to discuss, in particular, technical questions around the power-to-X technology. So that shall be as a brief overview on our association. I come now to a few technical aspects which I would like to discuss with you or share with you. The first, just show the different options we have when we are talking about power-to-X. It's not only hydrogen, but also a lot of other materials which are created out of hydrogen, starting with green ammonia, of course, but also then the different kind of hydrocarbons, and all these technologies are covered by our members. The big question at the moment at an international level is, and this is also very important for Europe, but in particular also for Germany, where is the hydrogen to be produced in future? Because obviously in Germany and probably also in Europe, it's difficult to produce all the huge amount of hydrogen which is going to be used for a future energy system. I took that picture from a recent study which shows that a lot of countries will be able already in 2030 to produce hydrogen at a competitive level. And as you can see here, India is one of these countries which could be able to produce hydrogen for roughly $1 per kilogram of hydrogen, and that means competitive because today gray hydrogen is dealt with worldwide with a price of roughly $1.5 per kilogram. By 2050, the situation will develop further on so that more countries are in the situation to produce green hydrogen at a competitive level. But for the upcoming decade, it's very interesting that these countries are rather limited, which means also that prime movers have a very good chance to be an important part of that developing market. What I would like to show here also is a potential development of the different technologies. At the moment, as you know, the worldwide hydrogen production is almost completely gray hydrogen. That will most probably change then in the upcoming years, where we see more and more blue hydrogen, but also then green hydrogen production. And you see here in 2030 that it is possible as I said already, in some countries to produce green hydrogen with a lower price than gray and also blue hydrogen. It depends, of course, very much on the regional situation, but if you remember the picture from beforehand, India is one of the countries where big potential is seen. And what you see here at that picture as well is that there are some countries which will be typical importers of hydrogen. That includes, of course, Korea and Japan. They don't have, if they are interested in hydrogen, they don't have the capacities to produce it themselves. China, Germany, and the US, you could replace Germany here also by Europe, which is a similar situation, not completely the same, but very similar. So these three regions will produce green hydrogen also by themselves, but are probably not able to cover their complete hydrogen demand. And then you have a few countries which are examples for countries which should be able to produce green hydrogen, also to export it to other interested regions. And India is not shown here in that picture from the mentioned study, but personally I would see India here, as I said beforehand, also as a potential candidate. Another very important question is where the hydrogen is to be used. And this is a very difficult question I can't really answer because at the moment in Europe, at least, the discussion is very controversial. From our point of view, it makes totally sense to use green hydrogen in the mobility sector, because the CO2 abatement costs here are that high that it makes sense from a market perspective to pay for hydrogen or other green energy carriers, while the other sectors like steel, for example, are those sectors where you don't have any alternative than green hydrogen to become decarbonized, but it's more expensive. So the mobility sector would be, from our point of view, a very good market to start with those activities. But as I said, the discussions at the moment are very controversial, and we probably will see in the next couple of weeks or months a decision in Europe and in Germany, most probably next year, how to deal with these difficult questions. So that is already the end of my presentation. I'm happy to answer questions, if any, and if you are interested in our network and our platform, please do not hesitate to contact us. You can see also our website at the very end. You see here me and my team, which is dealing with all these different questions covered so far. Thank you very much indeed.
Yes, thank you very much, Mr. Nath and Mr. Müller-Baum. Impressive number of Power-to-X members. And why is it so important to network with these German companies? Mr. Halusa has mentioned it. The German federal government is coming up with a funding guideline, and Indian projects are eligible for funding of up to 15 million euros if a German investor is on board. And this brings us to the next presenter. With us today is Mr. Chirag Shah, Chief Manager Siemens, who will give us insights into flexible, efficient, and scalable Megawatt PEM electrolyser technology. Floor is yours.
So, thank you very much, Tobias, and good morning to all the colleagues who have logged in from Germany, and good afternoon to all the participants from India. And I am really thankful to IGEF and IGCC to give us this opportunity to share the insights into the offerings that we can bring into the decarbonization for not only India, but globally. And from here, I would like to share some of the details about the flexible, efficient, and scalable PEM electrolyzer technology that we are able to offer from the house of Siemens Energy. So if you're able to view my screen, I think I would be able to take it forward and give you some more details about the topic.
Yes, wonderful.
Thank you. So what is Siemens Energy and what is new energy business? I think we at Siemens Energy realized and understand that decarbonization is really the need of the hour, not only in India, but globally. And to get into this topic, being a technology leader, I think we have had our engagement with the Hydrogen Council and the Fuel Cell Joint Undertaking Council right from the early days, almost a decade ago. And we have been into the development of the electrolyzer technology right from the early days and set up a pilot plant also at Germany at Mainz. I will tell you more details about this project also as we move forward, but one of the highlights that I would like to really share over here is that in the end of 2019, we also have been able to set up and commission one of our lighthouse projects at Linz in Austria, which is a steel plant, voestalpine, and that is where we have been able to replace the use of carbon emitting fuels with green hydrogen. And that is a project which I think is really a benchmark and one of its kind that has been set up globally so far. So coming back to what we can offer, I think having said all this, we at Siemens are capable not only of delivering hydrogen systems and products, but also the Power-to-X solutions, which our earlier colleague from Vdma was elaborating. And from the house of Siemens, I think we have the capability to deliver all the Power-to-X solutions that is required. And to begin with, I think in any project, every customer and every project needs energy consulting and a deep dive into the feasibility, which is also something that we can bring on the table. So I think having said all this, we spoke a lot about what needs to be done and why are we looking at all this and why is sector coupling really essential to achieve the deep decarbonization that we are all looking at. We all understand that globally there is a focus on setting up green renewable energy power all over the world. And what we can do from here is actually derive the green electricity or the green power and generate the green molecule, which is hydrogen, that we can use across the different sectors. I think Vdma already elaborated on the different sectors where we can make the blending of the green hydrogen to get really a deep decarbonization and reduce the emissions in the country. So taking it forward, I think the key was the renewable energy source, which is actually being set up globally and also in India. I think our Honorable Prime Minister has also set up a vision that we have around 450 gigawatts of renewable energy into the system by 2030. And if we have this kind of renewable power, which is intermittent and fluctuating in nature, then I think the PEM technology or the PEM systems are the best natural choice to integrate with the renewable source, because it not only has really good startup and shutdown cycle times, but also quite flexible to support the intermittent power supply for maintaining the good quality or purity of green hydrogen that we can produce. It also not only has cold startup capability, but also has the capability to give primary frequency response to the fluctuations of the grid. So looking forward, I think we said we are looking for decarbonization and green solutions. So PEM is, by its natural design, quite green in nature. It does not have any carbon emissions, unlike the other hydrogen producing methods like SMR. And what we use into this system is nothing but water, from where we derive the molecules of hydrogen and oxygen. And we are able to achieve a good hydrogen purity of 99.9%, which I think is good enough into the different derivatives that we want to produce. And of course, I think we don't have any chemical dosing into the system. So all in all, I think as a package, PEM is not only environment friendly, but also a competitive system, because we heard from our earlier speaker that globally we also foresee that the price of electricity, or the LCOE, what we call, is expected to go down by the next few years. And in case we are able to achieve that, I think below $3 cents per kilowatt hours, PEM definitely will be a benchmark in achieving the green hydrogen technology. PEM, of course, also has a very small footprint if you want to implement it within your existing premises. And from the earlier explanation, I think you would understand that the operating cost for the system is also quite low. What did Siemens do actually to get into this? I think, as I mentioned, Siemens started this journey almost a decade ago with a lab scale demo electrolyzer. And over the next 10 years, or in the last, let's say 10 years, we have been investing into innovation and research and development to get new products and more efficient systems into the market. Because going forward, I think we all know that efficiency is going to be the key in order to achieve the low cost of hydrogen that we are all talking as a buzzword in the industry. So today, I think we are in a situation where we can give a double-digit product into the market, which is a 17.5 megawatt Silyzer 300 that we have from the house of Siemens. And definitely the innovation and research and development does not end here. We have in parallel our activities ongoing to come into a 3-digit system over the next couple of years. And of course, by the end of the decade, we also look towards a giga scale development into the technology. So with this, I think I would only quickly give you a snapshot about the existing portfolio or the existing system that we have. It's a 17.5 megawatt PEM electrolyzer that we have, which comprises of 24 modules. And you can see from the picture over here that we have 4 series where the different modules are arranged, and we can achieve a system efficiency of larger than 76%. So I think as an output which everyone looks forward to, we can deliver around 335 kg of hydrogen per hour when we have the system operating at full load and full capacity or full utilization. So I think just to give you a quick glimpse into the technical details of the system, because I'm sure many of you would be interested and looking forward to having or adapting the green hydrogen production on a large scale going forward. So here is a quick snapshot of what is the system capable of delivering. I think I already mentioned we can deliver up to 335 kg per hour at an efficiency of more than 75%. And also as I mentioned in the earlier time, the PEM technology has a very fast startup cycle of less than 1 minute with a ramp rate of 10% per second to go to full load. So I think also on a comparative scale, I think the entire array or the system has a lifetime of around 20 years and the modules are interchangeable. And as a feed-in, I think what I mentioned earlier is that we need around 10 liters of dim water to achieve 1 kg of hydrogen with an extremely high purity of dry hydrogen gas. So with this, I think I would like to share also that this system is actually customizable and scalable to the needs of the requirement on a large scale, which I think we all believe going forward will be the requirement in the several industries. So the system here is, as I said, quite adaptable and scalable, where we can go into even a 8.5 megawatt configuration with 12 modules, or multiply it into multiples of hundreds of megawatts if we need a higher capacity, which not only helps in reducing the cost of green hydrogen that we produce because of the optimization of the BOP, but also gives you a good saving on the footprint that you would need in installing such a large capacity as per your requirement. And how do we achieve all this? I think I would only take a short time here to explain a little bit how the efficiency of the system is achieved and how does it vary. As I mentioned, we can have achieved the efficiencies of around larger than 76% if we have just the system or the PEM module. But if we have to factor in the entire cell as a system, where we have certain losses coming from the transformer and rectifier, probably we can get an efficiency of just less than 0.5% lower. And it also goes a little bit 0.5% lower if we want to add in the chiller and the cooler systems into that. And if we need a specific pressurized system, then I think efficiencies can be achieved at even greater than 72% and at 10 degrees Celsius. So I think this was just to give you a feel about how efficient the system is. Even if we load it into the full capacity, we are able to have very good efficiencies and deliverables of green hydrogen at full load. And here I give you a very quick glimpse, not to get into the technical details, but I just wanted to give you a feel about when we have a startup of the system. I think, as I mentioned earlier, the system is capable of getting to full production capacity in less than a minute. And when we have the initial startup from standby mode, I think it takes around 30 seconds by the time we are able to achieve 100% load for production. And then there is a purging cycle. So within a minute, I think we are able to achieve the green hydrogen production at the highest purity on the terminal point. And also it has a very quick shutdown cycle of around 20 seconds. But the main beauty which I wanted to highlight over here is that it also has a very good response to the intermittent renewable power source that you would feed into the system. And it can have a dynamic range of, or a ramp rate variation of 10% per second, which is so fantastic that I think no other system is able to deliver and support in this manner today. And you can go up to 5% minimal load as well. So that is the best part that we want to share with you on the electrolyzer, where we all know that today we are all banking on the green energy or the green source of electricity in order to achieve a performance where it can cater to the fluctuating source of electricity or power. So all in all, I think I would only like to summarize here by saying that we have a system which is extremely efficient, which is highly modular, which is maintenance friendly, which is scalable, and moreover, we have the possibility of even connecting it digitally, where we can give you remote support as well by taking the data onto the cloud. And I think, having said that, I would only take a minute more to explain to you that the electrolyzer is just one part of the entire power to X solution that I was mentioning earlier that we can deliver from the house of Siemens, because Siemens being into every foray of generation, transmission, and distribution, and the green hydrogen, I think right from the renewable energy from our Siemens Gamesa to the transmission products from our portfolio to the electrolyzer and right up to the derivatives that we want to have for our end use, we can deliver that along with a partnership that we can bring for your end use. To quickly give you a glimpse of some of the references that I was mentioning earlier in my presentation, I think this is the details of the project which we implemented at Mines in 2015, where we set up a small plant or a pilot plant where the green hydrogen produced was delivered to the nearby industrial companies and also fed into the natural gas grid because it was being tested on a pilot basis. And also they wanted to make a test case into the mobility sector. So we were also delivering the hydrogen into the refueling stations where they found that this application is really making a good value and meaning for the further commercialization. And here is the project that I was referring called H2 Future, which is a flagship European project where we implemented a 6 megawatt Silyzer 300 system into a steel plant where the green hydrogen produced was replacing the carbon based fuels for the steel making process. And also it was being used to cater to the grid fluctuations that were being felt into the system from the renewable source of power. So I think, having said this, I would really like to show you also in reality through a small video clip about one of our reference projects. So maybe, can we have the video clip, please?
H2 Future. Global CO2 emissions are to be almost completely eliminated by 2050. This presents major challenges to industry as well as to energy providers. Part of the H2 Future research project is aimed at discovering new methods for energy supply and thus opening up new prospects for the gradual decarbonization of steel production. The world's largest pilot plant for carbon-free production of hydrogen is being operated for this purpose in Linz. Up to 100% of the electricity required for this comes from renewable energy. The pilot plant has been used to test whether the technology deployed there is suitable for large-scale industrial production of green hydrogen. The potential of the hydrogen plant for providing grid services and the possibility for balancing fluctuations in the electricity grid are also being studied. The core of the new plant is a highly dynamic proton exchange membrane electrolyser with a capacity of 6 megawatts. The plant produces 1,200 cubic meters of hydrogen per hour. That is significantly more than in comparable systems to date. In electrolysis, electricity is used to break water down into hydrogen and oxygen. The hydrogen that is produced is fed into the voestalpine gas network. The long-term goal is to use the new technology to replace fossil fuels like coal or natural gas with green hydrogen. The new plant is currently the only one of its kind worldwide and is a technological lighthouse project. H2 Future, a joint project of Verbund, voestalpine, Siemens, Austrian Power Grid, K1 Met and TNO, supported by the European Union.
So thank you very much, dear colleagues.
Thank you very much, Mr. Shah. Very impressive. There have been already quite some questions in the chat. We'll get later to this. I think all of our presenters have agreed to share the presentations. So whoever registered for the event will be able to receive the presentations. But before we come to the discussion and to the questions, last but not least, Mr. Jay Prakash Soni, Senior General Manager and Head of Process ThyssenKrupp Industrial Solutions India, will give us insights into large-scale modular alkaline water electrolysis technology for green hydrogen plants in India.
Yeah, thank you very much. And good morning and good afternoon to colleagues from Germany and India who have joined. Myself, as explained by Mr. Tobias, thanks for the introduction, is working in the organization ThyssenKrupp. Just a small question, are you able to see my screen? My presentation, are you able to see before I move forward?
Yes, but if you could switch to presenter mode, I think you're using two monitors.
I have used the presentation mode already. Are you able to see now, or?
Yeah, if you could go up and switch the monitors, that would be fine. Right, you see this end slideshow on top, and on the left of it there is the possibility to switch the monitors. Yeah, display settings, correct. And then switch, please. Click on it, please, and swap. Yeah, wonderful.
Yeah, okay. Sorry for the technical glitch. Okay, so good afternoon and good morning from my side once again. I will take you through the capabilities and the let's say from our company ThyssenKrupp regarding production of this green hydrogen via this AWE technology, what we call is alkaline water electrolysis technology. Just to move forward, a small intro regarding our company. Our company is ThyssenKrupp Industry, which is the big conglomerate of various industry and various fields, starting from steel, automotive, and submarines. But what is interesting today for today's presentation is the plant technology, where we built the chemical technology plants for worldwide. This chemical plants are being built by the company in Germany, in Dortmund, ThyssenKrupp Industrial Solution, which has the business unit called Ude. You might be familiar with the old Ude technologies. We are present in the various chemical plant fields, starting from let's say fertilizers, electrochemical plants, the coke oven plants, and large scale plastic industries. The one which is connected to today is on your left bottom, which is covering big hydrogen plants. Of course, they were starting from the gray route, and the electrolysis plant, where we are now talking today to produce or utilize the green electricity produced. So these are the two vast field where we have built umpteen number of large scale plants, both for hydrogen, downstream of hydrogen, and for electrolysis, which I will just explain in detail in few subsequent slides. Just before I start, intro about our company in India. I belong to the company which is the subsidiary of Dortmund here in Mumbai, running for last more than 4 decades. In Mumbai and Pune, we have in two offices actually, and we have built more than 800 projects for India and globally. Coming to the topic for the discussion today, the electrolysis. The electrolysis part of the, let's say, various chemicals like sodium chloride brine or sodium potassium chloride brine. We are in this field for more than 50 years, actually. For this, there is a joint venture between ThyssenKrupp and De Nora called ThyssenKrupp Uday Chlorine Engineers, wherein the technology part is developed by the ThyssenKrupp, and the cells are manufactured by the company De Nora Industry in Germany and Italy. And of course, with the help of this and ThyssenKrupp Uday Chlorine Engineer is the market leader for the electrolysis plant, be it the electrolysis to produce caustic soda and chlorine from the brine NaCl solution, or utilizing the hydrochloric acid electrolysis to produce the chlorine back into the system. So the electrolysis which we are talking today to electrolyze water and produce hydrogen is very much similar to this technology. So as I just mentioned, because of the electrolysis experience for these two different technologies of chloralkali as well as hydrochloric acid electrolysis, we have developed this alkaline water electrolysis in the module, which we will talk in more detail. But the experience which has been gained by these two technology over the last 50 years is not less than 10 gigawatt of equivalent installed power. The elements or electrolyzers which are installed worldwide are contributing or accumulating to the let's say level of 10 gigawatts total capacities. As far as the production is concerned, we can produce up to more than 1 gigawatt capacities equivalent per year, basically, and more than 600 installation of this electrolysis plants are already there of various capacities, starting from 20 tons per day up to 2,000 tons per day capacities. So this experience has been directly, let's say, transferred to the water electrolysis module. So we are able to offer right from day one high reliable elements or the electrolyzer design. Of course, this operates close to atmospheric pressure, so it is quite safe. The size of each element within this electrolyzer is high. I mean, I will say close to 3 square meter. So that gives the let's say production higher production. So the footprint requirement is reduced drastically. And of course, the need of the day is let's say less construction. So it comes as skid mounted facilities already, so which is ready to install at site. And as I explained, more than 1 gigawatt capacity we have annually for the production. So the mass production can be delivered at a very fast rate. And of course, when we are talking about the operation, the let's say the control system and the safety is utmost, which is taken care properly. Just to explain the concept, how does it work? Basically, when we talk the alkaline water electrolysis, it is nothing but the electrolysis of alkaline solution, which is KOH, this potassium hydroxide. So we have this cell or the cell element where we let's say electrolyze this KOH, and by passing the electricity through the direct current, we produce let's say from this KOH hydrogen on the cathode side, that is on the negative side, and oxygen on the positive side. And this KOH is recirculated back, which is topped up by water. So if you see the overall reaction, it's electrolysis of water, which gives us hydrogen as well as oxygen. So this is for the concept, but how to bring it to the reality? In the reality, we have the design of this cell, which is very much similar to our caustic or the caustic soda chlorine cell, made of complete metal. On both the side is made of nickel, basically cathode and anode, and it is separated by a small by the diaphragm or membrane to have the partition between cathode and anode compartment. And this design is the well-proven zero-gap design of chloralkali experience. And as I mentioned, nickel, it's made of complete nickel. So how do you translate this one element into the one electrolyzer module? So here you can see this is one module this is the module of one electrolyzer which is having almost close to 300 elements in one electrolyzer. So this module is let's say able to process 20 megawatt of energy. So this is a 20 megawatt module which has a very high stack efficiency of 82% almost, and the power to generate per ton of nm cube of hydrogen is about 4.5 kilowatt hour per nm cube. We get from the module quite high purity, 99.95% from the electrolyzer directly. And of course, after the purification like deoxo and PSA treatment, we can go up to 99.4 or 3 digit as per the need from the downstream requirement. Of course, it is available. Availability is quite reliable and very, let's say, long time availability. More than 98% it can be made available throughout. The cell life is very high. It is also quite fast reacting on the power flexibility. So that whenever you have the fluctuation in the power daytime or nighttime based on the renewable energy availability, this can be ramped up and ramped down very easily. The technology is reliable, as I said, because it is coming out from the decades of experience on this kind of technology. It's fully automated operation, very less manpower required, and of course it can be turned down to 10% capacity level for the hot operation. The ramp up or ramp down from 10% to 100% or down from a hot system, it can be done within 30 seconds. And of course, from a cold start to the coming up to the capacities take half an hour and slightly more than half an hour. So this is how this 20 megawatt let's say one electrolyzer module look. Of course, this is completely modularized, and we have standardized this 20 megawatt module in order to get the let's say multiplication for the higher capacity quite easily. So we have this module which has the elements of the cell or the electrolyzer cell element, and also the downstream and upstream equipment connected to this module. So this complete set is forming one electrolyzer module. And of course, since this is a modular and easily let's say expandable, you can do the scaling for the plant very easily. So from 20 megawatt, if someone wants to go 100 megawatt or 200 megawatt, it's just simply the replication. And because, as I mentioned, it is coming in the skid mounted modules, it is easily possible to do the construction at site at a very short time. This is just a glimpse to elaborate the capacity expansion possibility. So if you just simply multiply the number of modules as per the capacities required, so you keep on adding the electrolyzer modules one after the other, and we can achieve the higher capacity. And downstream and upstream, which are just located beneath or the opposite to the cells, this can be also expanded very easily. So this gives a very good model for going for a mega or large scale capacity plant. coming to the requirement, is the hydrogen or the green hydrogen only thing required? As mentioned in the earlier or starting presentation, the decarbonization or the coupling of this hydrogen with the downstream chemical is very, very crucial for the economy of this hydrogen. Simply because the transportation and the let's say the value addition becomes very easy once we convert this hydrogen molecule to the further chemical modules, basically. So just to elaborate, if you have any part of the renewable energy can be converted into the green hydrogen, and then this green hydrogen can be combined with various technology which we have already developed and demonstrated with numerous plants to produce the green methanol, the green ammonia, which can be further utilized to produce urea and going for the fertilizer as a green chemical completely, or the methanol, which can be used to the downstream refining and the further let's say fuel applications easily. So the transportation and selectivity or the utilization of this green hydrogen becomes very, very powerful. So our experience can be combined here too. Just to give you one or two couple of examples, in the first presentation of Power to X, we just saw a short summary about these let's say downstream chemicals. So here, as I just explained, the electrolysis, which is producing green hydrogen, can be combined with any CO2 which is coming out of the emitting industry like steel industry or cement industry, and this carbon can be captured to form the methanol along with this green hydrogen, and which can be used as a green methanol directly. Also for the ammonia, as I mentioned, so we combine the green hydrogen coming out of this renewable energy and the nitrogen from the air, and you get CO2 neutral ammonia, which is today produced via the synthesization of fossil fuel, basically, in all over the world. And this ammonia can be further let's say clubbed with the CO2 coming out of the carbon emitting industries to form ammonia, urea, which can be utilized as a fertilizer, as a green fertilizer without any hesitation. So these are all about the technology or the experience which we have, but the proof is in the form of the actual installation. So since this technology has been developed in Germany over the period of long experiments, the pilot facility was installed at our own ThyssenKrupp steel plant in Duisburg, which is called Carbon to Chem project. Here what we have done is we have installed this 2 megawatt electrolysis module in that complex to produce hydrogen, and this hydrogen was produced by the energy or renewable energy in that area by wind energy produced. So this green hydrogen was combined with the let's say synthesized gas coming out of the steel industry to form methanol. And we also produce in this plant ammonia by taking the nitrogen from the air. So this is the demonstration facility which was installed right back in 2018 or late 2018, and since then it is working perfectly in that complex. So based on this experience, of course, we didn't stop and kept on continuing, and I will share with you some of the projects which we have won or which we are currently executing all over the world. That is only the few plants list apart from the complete list which I am sharing with you today. And these are all large scale or the mega scale plants which we are able to produce from our technology. So the first one is from Canada, wherein we are executing in the early engineering phase the green hydrogen from the hydroelectricity renewable energy form. And the capacity of this plant is to capture 88 megawatt module. So from our system, it is installed. This green hydrogen will be utilized to produce green methanol, ethanol, and other biofuels, basically. And the oxygen which is coming will be used to incinerate the waste from the city, basically. The next plant is in America, USA, Donaldsville, where we have already built a big fertilizer complex some years back. And in order to utilize the green power or decarbonize their facility, they are installing with a small electrolyzer as a test case, which is the 20 megawatt module electrolyzer. So we are installing one module there in order to utilize this hydrogen and produce ammonia, and this ammonia will be utilized directly in their ammonia complex. Of course, this is a smaller capacity as compared to the complete ammonia production facility, but after this demonstration, they will be adding in the future more number of modules here, basically. Coming to the Saudi, where, as you know, there is a huge availability of solar power and also wind power. So here we are installing one module. Originally, it was thought of 10 megawatt, but now we are let's say doing engineering to change it to 20 megawatt module directly. And this module, after installation, will be helping us in the, let's say, demonstration, and the total capacity or the expected capacity of this complex is in the tune of almost 2 gigawatts. So you can imagine the utilization after the completion of this project. Yeah, just I explained. So after the testing or the completion of the previous electrolyzer, this we have already started the early engineering, early part of the engineering, but at the end the capacity will be in the range of almost 2 gigawatt. So just to summarize, the hydrogen is which is currently associated with high carbon emission because it is currently produced via the gray route from the fossil fuel in major part of the world. But with the, let's say, help of this renewable energy utilization and water electrolysis, I'm sure this industry of green hydrogen production can decarbonize the complete hydrogen production. Not only that, this is a very good source of, let's say, energy storing or transportable, either in the form of self-hydrogen or after the conversion of this hydrogen molecule to the downstream value-added molecules. It can be very much helpful, and not only helpful, but it will help in achieving the decarbonization of the complete sector. And of course, ThyssenKrupp is the front runner for the technology, not only for the hydrogen, but also for the, let's say, based on the experience, our experience from the various electrolysis designed for chlorine production or hydrogen production. This technology, of course, is reliable, high efficient, and it is because of this 20 megawatt module, higher capacities can be achieved by simply multiplying these modules. Not only this, ThyssenKrupp, with the let's say experience of the downstream products like ammonia, methanol, can easily couple this green hydrogen to produce green chemical molecule downstream. So that's all. This is coincidentally the year of celebrating 100 year of our foundation. Our company in Germany has already completed 100 years this year. So thank you very much for your attention, and I am open for the question at the end, as Mr. Tobias said.
Yes, thank you very much, Mr. Soni G. Impressive. And this directly brings us to our Q&A session. There have been quite some questions in the chat, and maybe we'll start right away with Thyssen and Siemens on project sizes. you had shown that you're working on a 2 gigawatt electrolyzer capacity being under development right now. Siemens has shown electrolyzer projects more in the megawatt category. The question was largest green hydrogen plant you have commissioned so far, and if there is a maximum in terms of plant size. Definitely you said all your technologies are scalable. But yeah, question to you, maybe we'll start with you, Mr. Soniji. This 2 gigawatt electrolyzer capacity is under development and will be commissioned. And do you see any limits in terms of upscaling?
Just to give you the answer, maybe one by one. So you asked the commissioned one. So commissioned is our 2 megawatt module, which I just showed in the Duisburg facility. And the 20 megawatt and 88 megawatt, these two projects which we are, let's say, under the engineering phase, will be the target to complete by early 2023. The 2 gigawatt module will, of course, go in phases, starting first with 20 megawatt, and then it is slowly going up with in the step of let's say 100, and then 500, then 1 gigawatt, and then 2 gigawatt. That's the capacity, and the target for achieving this is, I think, 2028 or 29. During that time will be achieved, complete 2 gigawatt. Yeah, but of course, as the design is concerned, it is easily scalable, and 2 gigawatt also is not the limit. I will say we can multiply more if needed. So
Siemens, we heard you have the largest electrolyzer stack available in the world, but in terms of plant sizes, maybe same questions to you.
Yes, Tobias, I think I already covered it in my presentation, where we already showed the reference of a 6 megawatt installation of electrolyzer in a steel plant at Linz in Austria. So that is, let me say, the largest system that has been installed and in operation today that we have from Siemens. And of course, on the lower side, I think I already also explained when I was sharing my presentation that in the past we have done even small sized or lower capacity installations, even up to lab scale. But I think that is something which is of the past, of the last decade. And I don't think that anyone would like to continue that legacy going forward when we are talking about large scale productions.
Well, there had been some questions in the chat of what would be the smallest project size Siemens and Thyssen would be willing to implement in India. So do you have a smaller electrolyzer than the one presented? Mr. Shah, I think you presented the stylizer, no? 300. Wasn't there also an 8 megawatt electric version?
Absolutely right, Tobias. I think you heard me quite well, and I'm really happy to recognize that. So that is what I explained also during my presentation, that the Stylizer 300 has a configuration where we can even give a half capacity of around 8.5 megawatts, where we can use it with 12 modules. And that is the lowest capacity that we would be able to deliver to any of the applications that we see here.
Good to know, thank you. And Mr. Soniji from Thyssen Group side, what would be the smallest project size you would be willing to implement in India?
In India, I will say 20 we should start with, because that's a really nice capacities which we have seen. That is why we have standardized this. Of course, we can offer, I mean, as I demonstration plan, it is 2 megawatt, but the viability consideration with the downstream and upstream system is a little bit lesser. So 20 megawatt is a good size module to start with, because it gives around 4,000 cubic meter of hydrogen with one module production.
Yes, thank you very much. May I request Mr. Müller-Baum and Mr. Rajesh Nath also to join us for this Q&A session? Question to the VDMA would be, where do you see the project size getting towards to? I mean, definitely it's getting bigger and bigger, but is there something like a typical green hydrogen plant size in Germany, for example?
That's very difficult to answer because at the moment we see only pilot projects, research projects, and so on. The market is just developing. Yeah? For the future, my personal feeling is that we will speak about projects in the large megawatt or more probably gigawatt scale. But at the moment, in the upcoming years, we may see projects on, I don't know, 100 megawatt, 200 megawatt. But at the end, of course, the size matters here very much, and I guess we will see more and more gigawatt projects.
That brings us, thank you very much. That brings us directly to the next question. There had been a lot of questions around the Capex, OPEX. So maybe we'll start right away, continue right away with you, Mr. Müller-Baum. What drives the cost down for hydrogen? Is it more the Capex investment, and there you see that the costs are still coming substantially down? Or are you saying 40, 50, 60 years of development, there is not too much space anymore? And then cost of electricity, is that the main driver, or is it more the full load hours over the year so that the electrolyzer really runs the whole year through 8,000 hours plus? So what is it? Is it Capex? Is it electricity? Is it full load hours? What drives the cost down?
Yeah, at the moment, Capex is of course a very important question, but we see a significant decrease of Capex costs due to the technical development, and we expect huge technical development in the upcoming years. So far, it's not the technology itself, but the matter of large-scale projects and the matter of production costs for components and the plants themselves. So let's consider the Capex costs not that relevant any longer in 2025 or 2030. At the end of the day, the OPEX is the most important cost driver here. And first of all, we have to see the electricity, the cost for electricity. When you see that worldwide there are already projects calculating with electricity costs below 1 cent, euro cent, dollar cent, it doesn't really matter, below 1 cent per kilowatt hour, that's the benchmark in a sense for cheap green electricity to come up with a low price for green hydrogen. Also relevant are the transport costs. Are you producing green hydrogen for local use or for worldwide demand? Because if you have to transport it, you need to calculate the transport costs either with a pipeline, and then it's typically just a region around your own site. If you want to ship it, for example, from India to Europe, you need to calculate also the shipping costs. And then from our point of view, we think we are more probably talking about ammonia or other hydrogen products than the pure hydrogen. For the pipeline is the cheapest way of transporting it, 2,000, 3,000 kilometers, but for longer distances, we will see shipping transport in future. I hope that answered it roughly sufficiently.
Yes, thank you very much. I'm actually really thankful that you pointed out the aspect of transport, because the next hydrogen session IGCC, Indo-German Chamber of Commerce, and IGF have planned will be on transport of hydrogen, where we compare cost of shipping via the ammonia route versus pipeline, or versus direct electricity transmission via HVDC lines. But there was one small question in terms of full load hours over the year. Do you have a feeling about what projects in Germany look like right now? Do they run 8,000 hours plus, or is it more like 50%? Do you have an idea, specifically talking about green hydrogen electrolyzer?
For Germany, the question is almost impossible to answer, because it depends very much on the legal framework, which is currently changing. So let's consider that question more regarding the matter of the market situation and the technology impact. What I learned from our members is that you should have not necessarily the 8,000 hours per year, but at least 4,000 hours. The more, the better. So I guess we will see more projects calculating with, I don't know, 5,000, 6,000 hours per year. But the 8,000 is really something you will only be able to cover in very, very limited regions worldwide, where you combine wind and power for the production of green electricity.
Yeah, thank you very much, Mr. Müller-Baum, for shedding some light on these aspects. Maybe directly continuing with Siemens, did you do some calculations on the cost per kilogram hydrogen from renewables in India today? Are you able or willing to share some insights on Capex costs of electricity, full load hours? What are your assumptions for some on-the-ground projects in India right now?
Yeah, Tobias, that's a very interesting and challenging question as well, because I think on the ground in India, we really do not have as many projects of green hydrogen so far. What we see in the market today, at least from the first visibility, is only some pilot projects which are being announced and launched by some of the public sector companies or utility companies or oil and gas companies and so on. Of course, there is growing interest also from the private sector equally strongly here in the direction. But I think we are still far away from really taking a discussion level of, what could be the cost of hydrogen from green energy in India as yet, because I believe personally that there are still a lot of topics and framework as far as the regulatory topics are also concerned that need to be in place in order to really come to a good calculated number on the cost of green hydrogen. Otherwise, today there are several dynamics that are available, as Mr. Müller-Baum explained, that these are all dynamics that really are not clear for India so far. So I think we are still a step away from really calculating the cost of hydrogen or green hydrogen in the topic because of the different elements that I just explained.
Thank you very much. I was really impressed, Mr. Müller-Baum, by your slide from Bloomberg New Energy Finance. That was quite optimistic. I think you showed us India being able to achieve around $1 per kg hydrogen, green hydrogen, in 2030. I guess mainly because of low cost of solar by then. So that is not too far distance from now, no? So if we think of a project development time, I don't know, Siemens, what would be a typical project development line? At least 3 years, I guess. I'm not sure. So that means if we reach around $1 per kg, that means we really need to start to think about some projects on the ground right now. What's your take on this, Mr. Soniti?
Yeah, that is true, actually. I just want to add to Mr. Muller and Mr. Shah, the cost is, I think, more dependent on the OPEX here, basically, because we are consuming a large amount of electricity for producing this hydrogen. So to the tune of 65–70% cost will be coming out of the OPEX cost rather than the Capex cost, I will say. But you are right, if we are able to go to this level of Mr. Mullerbaum, what he showed, $1, I think we will have a lot of projects to execute, and we will have difficulty because that will be even cheaper than the gray hydrogen route somehow. So yes, of course, but it is going in that direction, because earlier, if you remember, a few years back, nobody was believing on the power from the solar, let's say, affordable. Today, the costs are coming so low that even it is beating the coal based power generation. So I am sure this route also will be quite attractive in coming years. Let's hope for that.
Maybe I can
thank you very much. Yeah, Mr. Müller-Baum, please.
Sorry, maybe I can add some one sentence, because this is, of course, the question how it works in reality. Yeah, what I've shown here is just a study. It gives you an indication about the potential development of costs for electricity, and then depending on the electricity, the hydrogen. At the end, it depends very much on your local situation and on the concrete project planning. And of course, costs doesn't mean necessarily price. Yeah, that's also something we shouldn't forget. That at the end also market, the matter of the market. But it shows, and that was the important point from my perspective, that India is one of the countries which should take the chance to produce hydrogen not only for internal use but also for export, because you may be able to benefit from a worldwide market here. That is an interesting matter from my point of view.
Thank you very much, Mr. Müller-Baum. There was one question related to Capex again, because I think ThyssenKrupp Group is speaking about alkaline, so there the cost reduction potential is not that big anymore, or do you still see a lot of cost reduction potential? While Siemens is talking about the PEM electrolyzer technology, where I feel a lot of companies are still standing at the very beginning of the development, so more cost reduction potential is there. So maybe you could shed some more light on this in terms of potential for Capex reduction.
Yeah, in principle, it's of course right that the potential for cost reduction is higher for the PEM electrolyzers than for the alkaline electrolyzers, just due to the fact that the PEM is a newer technology. Nevertheless, from my point of view, but maybe the colleague from ThyssenKrupp can evaluate that better than I can do. Also, the alkaline electrolyzers has some potential for cost reduction due to the matter of production. Yeah? If you consider large-scale automatic industrial production, the costs for the plant components becomes, of course, lower, independently of the development of the technology itself. So from my point of view, this potential for cost reduction Capex wise relates to both technologies from today's point of view.
Thank you very much. Mr. Nath, you wanted to give your perspective for hydrogen projects to be implemented in India underground.
No, I just wanted to share some statistics on the Indian scenario. As per the Central Electricity Authority, actually the aim we are talking about green energy, renewable energy, to increase it from 18% to 44% presently, and reduce the dependency on thermal energy to 52%. And all this would require Tobias a funding of about $1.4 trillion till in the next 20 years. So I just wanted to share this data or statistics.
Yeah, thank you very much. Continuing to talk about OPEX, I see there's a lot of technical questions, maybe to Siemens. Electricity consumption was one question. Mr. Shah, you had shown some specs. Here again, the question of kilowatt hour per electricity consumption of the silyzer itself, but maybe also of the entire process. So how much is being consumed by the silyzer per kilogram hydrogen, and how much electricity in total is being consumed to get 1 kg of hydrogen?
Yeah, I think Tobias, definitely this is a technical question, and I would like to explain it in a little different way, because a lot depends also, as we discussed, upon the utilization factor, that is the full load or partial load that we want to use the systems. So definitely the kilowatt hour per kg consumption of electricity also would vary based on the load that we have on the system. But if we want to really look at it in a measurable way, or if we want to really look at what would be in real concrete number terms, I would say that definitely we can have a 50 to 55 kilowatt hour per kg range of electricity or energy consumption if we are able to utilize the system in a big way.
Mr. Soni ji, are you able to give some insights into electricity consumption?
Yeah, of course, as Mr. Shah said, it lot depends on the configuration of the plant, the utilization and all. But in general, let's say if we are utilizing to the extent or the max extent possible, as I presented in my one of the slide, the electricity consumption is in the tune of 4.5 kilowatt hour per meter cube of hydrogen. So that is kind of a base figure we can consider. But of course, based on the design configuration, the current densities applied to it, it may vary a little bit up and down. And the rest of the energy which is required is for the upstream and downstream system. Like if someone, because the production of hydrogen, as I mentioned, is at close to atmospheric pressure here. So if someone needs the hydrogen at 30 bar or 100 bar, the consumption of energy will depend on that. Like in Europe, grids are consuming at close to 100 bar hydrogen, where they are supplying and to the system. Or if there is a plant production needs 20, 30, 40 bar, this will have a slightly different consumption. This is one part. And second consumption comes from the, let's say, deionization of water, because you need very high or ultra purity water, which comes from the deionization. So that also consumes some part of electricity.
Yeah, maybe you can shed some more light on this. I don't know, or Mr. Müller-Baum. So you have the entire plant and let's say abundant renewable energy sources, and 6,000 full load hours are maybe possible. How much electricity is actually being consumed by the electrolyzer itself, and how much by the pumping system, by the cooling, by all the auxiliary services around this electrolyzer? Is it that the electrolyzer actually consumes 95% and we can just forget about the rest, or is it that actually we have to consider a lot of auxiliary systems to be powered by electricity also?
I'm pretty sure that the two colleagues from Siemens and ThyssenKrupp can answer that better than I could do. My personal feeling is that the electrolyzer itself is the main consumer, but I can't say it in a percentage figure.
Mr. Shah and Mr. Soni will again say it depends on the size of the plant and the configuration.
No, Tobias, I think my answer was very simple to this question, and I already explained it in my presentation when I was showing how the efficiency would change depending upon what are the auxiliaries or the equipments that you keep adding on. And if I just take a step back and a flashback, I think we already shared that we can achieve efficiencies of larger than 76% in our system or in our module. But when you have the transformers and rectifiers, I think I explained we can have 0.5% loss in efficiency. And then if we take it further and if we add the cooling system and the chiller, there is another 0.5% loss. So overall, I think I just wanted to give the impression that as many equipment or auxiliaries that you keep adding into the system, I think there will be a little loss due to the energy consumption and the heat. So that is how I think the entire configuration of the plant or the design of the system can be carried out. And each technical details can be worked out accordingly. That's how I would explain this entire phenomena.
Thank you very much. There's a lot of questions actually in regard to PEM alkaline. Maybe one question, if you allow, environmental impact of the technology. Is there anything we should know about PEM and alkaline in this regard? Maybe Mr. Soniji, you start.
Yeah, environment, it is quite safe to operate. I mean, the hydrogen which is produced is in the closed loop. And of course, since we are not utilizing any carbon content, so we are not damaging the atmosphere at all. The energy or the electricity which is used is coming from the renewable source. So there are no emission from this plant because we are not emitting any chemical to the environment. Of course, the KOH which is used in the circulation or in the electrolysis loop is the closed loop cycle. So there is no loss of KOH or anything like that. And of course, this hydrogen and oxygen which is produced are going as a product or as a gas of very high purity. So there is absolutely no damage to the environment, I would say. Maybe Mr. Chirag, yeah, if you want to add something.
Yeah, I think here the answer is quite simple for me, because what we have in our system is actually just green electricity and water. We don't have anything else beyond this into our system at all. So what we have as a production is only the hydrogen and the oxygen. And we also don't need any chemicals into our system as far as the hydrogen generation is concerned. And neither do we have any nitrogen into the operation of the plant when we are producing green hydrogen. So all in all, I think from environment standpoint, I would say that our system is completely green and environment friendly, which operates only on the natural resources of wind, solar to give green electricity, and water. That's all.
Thank you very much. Maybe we can ship in Mr. Halusa if he's still on board for final round of discussion, and maybe Mr. Müller-Baum, I don't know if you are able maybe to share your slide again on the merit order curve of hydrogen offtake depending on the CO2 price per ton. I think that was a very important slide, very impressive to many of our participants, because that seems to be the merit order curve for the off-takers, at least in US and Europe, I guess. But India might not be too far away from the same off-takers in industry. Yeah, Mr. Halusa, you heard it. There's mixed feelings about the future of hydrogen, at least the near future of hydrogen in India. Even though India has abundant resources in terms of solar energy, in terms of water, I think you don't have that much constraint if you even use the electricity for desalination. But amongst your members, Mr. Halusa, I guess Linde is also an important member. Is there discussions ongoing in the German Chamber? Are you in contact with the German Ministry for Economic Affairs and Power regarding these funding guidelines? You have spoken about that Germany is interested to bring down the cost of hydrogen on a global scale, and maybe even in a distant time, even import hydrogen. So maybe you could shed some more light on it. What is it all about, government of Germany pushing in the global hydrogen economy? And is there member companies of the IGCC involved?
Yeah, thank you, Tobias. And I would like to start by saying I've hardly ever been to a webinar where questions came in and in such a great number and such a great speed. So obviously the topic is of great interest, and obviously you nailed the topic right on the top, because again there were questions coming in from the very first minute. Thank you very much for that, and for the details also that all of you went into. Regarding the hydrogen, I think Mr. Müller-Baum made the point that India is in a very favorable position, actually, due to the expected cost levels of production. That there is the opportunity and the possibility to basically not only use it for decarbonization of the industry in India, but also to export it, because the price and cost level is competitive. And Tobias, you mentioned it as well, that there should be an abundance of renewable energy production and or at least potential for it. So that, I think, are very good. That's a very good base for moving things forward. And yes, of course, we have been in discussions. We've been in discussion with Siemens as well, because as you mentioned at the beginning, or as we discussed at the beginning, there is this Exportinitiative Energie, and by the German Ministry of Economy and Energy. Of the overall amount, I think it's somewhere between 20 and 25%. So to be exact, 2 billion out of 9 billion that is the overall funding for the project should go into partnership projects outside Germany. I think Mr. Müller-Baum showed the slide and showed Morocco, which is one of the partner countries. I think that has already been decided. Another one is Australia. But still there's a lot of opportunity, and we would and to utilize it. There are certain preconditions, and this is all described in the funding guidelines, and we're very happy to share that, to have a discussion with interested companies, and you mentioned some of them, but also in the audience, where there are projects that are being envisioned at this point in time, or even already in a more concrete planning process, to pick up the topic and see what we can do. There is the necessity of an investment, an equity investment into a project. There is the requirement of a German partner in this project. But again, if there isn't a concrete interest, we're very happy to pick this up together with the Indo-German Energy Forum, and move this then forward towards the ministry. So I can only encourage the participants to get informed and then contact us and see what we can do, and whether we can also formalize a more stringent partnership here between India and Germany, for that matter.
Thank you very much for your encouraging words. And yeah, that brings us to the slide I was just mentioning. Maybe you can once again shed some more light on this, Mr. Müller-Baum, because you have an idea on which international projects are actually coming up. And that was also a very important question in the chat. Where do you see hydrogen offtake coming up anytime soon? You might know that in India we are talking a lot of quotas in the ammonia and chemical sector, but we have also heard from Siemens about the steel already, very encouraging. So on this slide yourself, you're showing that actually with the carbon price already below what we are having today, it makes sense in buses and trucks. Cars is still a topic. I thought in Germany this is more something perceived as something which Japan and India still is following, but not Europe anymore. But maybe you have members in your Power to X group and you're not allowed to give a comment on this, but yet please shed some light on it.
Yeah, let's start with a process industry, steel and chemical industry, because this is of course an industry without any alternative than hydrogen to become CO2 neutral. And in that regard, the regulator, at least I can say that for Germany and Europe, is in the situation to change the legal framework in order to allow a green production of steel and also in future for the chemical industry. But that won't be a no-brainer in order to become competitive. With a fossil energy, of course, steel production is cheaper. In that regard, you need a CO2 price. And what you see here in the slide is, yes, indeed, the $50 per ton CO2, but for 2050. So the technological development and also the price or cost development in the future is already taken into account here. For today, this is of course not the fact. I'm pretty sure that in Europe we will see regulation coming up in the next few years that will not only allow to use green hydrogen for the steel production, but to enforce the steel companies to do so. And the CO2 price is, of course, a very efficient measure to achieve that. For the other sectors, like the mobility sector, for example, or the transport sector, you're of course fully right. The discussion in Europe is going to push the battery electric mobility that much that everybody forgets about other options like hydrogen or even e-fuels. But so far this is still under discussion, and we just want to use that slide here to make clear that from a market perspective, it might be much better to allow the mobility sector to use hydrogen and also hydrocarbons to become defossilized in order to push the market ramp up also for other industries, because at the moment we don't have the market competitiveness with regard to fossil energy carriers. That's the point here. It doesn't mean really we will see a huge market for fuel cell cars, for example. I personally believe that it will be the case also in Europe to see fuel cell cars, but at the moment it doesn't look like from a legislature's perspective. So it's a little bit tricky to discuss a lot of ifs and whens here with regard to the upcoming future.
Yeah, thank you very much for shedding some more light on this. I think we are well in time, but this brings us also to an end. Maybe I can request our speakers to just switch on their cameras, and let's maybe have a final round of statements about hydrogen economy, future of the hydrogen economy in India. Maybe we'll start with you, Mr. Soniji.
Yeah, so first of all, thank you all for participating in this nice workshop organized by IGCC, which gave us the opportunity to broadcast our capabilities, and also there was a quite good, interesting discussion also, as Mr. Halusa mentioned, that a lot of interest which is gathered, let's say, momentum on this green hydrogen. And I'm sure this green hydrogen is going to be a new buzzword, or as they are already mentioning, this is the next oil of industries. So in India, as Mr. Mullerbaum said, there is a huge potential, and we are seeing in last few months there are several players who are trying to build or trying to go ahead in this direction. Of course, this will take some time because of the fundings or the capex or other details to be finalized. But I'm sure this will go very long way, and there are technologies, whether you call it AWE, which is having large experience, or PEM, all technologies will have, let's say, a long way to go, whether in India or abroad. And green hydrogen will definitely be a chemical or the molecule for decarbonizing the whole downstream chemical industry also, in my opinion. So that's my view.
Thank you very much, Mr. Soni ji. Mr. Shah?
Yeah, I think Mr. Soni already said it all, but I would only like to add some more meaning into the topic by giving a view that, of course, we all strongly believe that with the decarbonization initiative catching up globally, and India also being a signatory to the COP21 with a commitment to reduce the carbon emissions, I think slowly but steadily India also will catch up on this topic. And we have very good and strong ecosystem that we can support all these topics and can really help putting it in together. Because we have the vision of the renewable power that is really catching up at a very good speed. We have the good infrastructure, we have the good government vision to focus on the green hydrogen topic also going forward. So I think with all the support mechanisms in place, we strongly believe that India will really shape up in the topic of green hydrogen, and we will be able to very, very clearly contribute to the reduction in carbon emissions globally.
Thank you very much. There have been definitely a lot of questions, more questions, technical questions for Thyssen and for Siemens. I think you allow that we share your contact details, presentations you have already agreed to share. So never mind everyone interested, please get in touch with the speakers. And let me maybe in between share one slide with you. Are you able to see this slide right now? So maybe for our German friends to understand, India has mainly base load solar energy. Yeah, this is something which is hardly to believe that coming from a German perspective. If you see that we actually in the winter months going down to maybe 2-3% of solar production, and then going up to 50% and more solar only in India, that is wonderful. But we need to speak about large scale storage, seasonal storage. India has 365 days of solar radiation at a factor of 2, which means that compared the worst day with the best day, yeah, it's 50%. Yeah, so US is also quite fine compared on a countrywide average. But in India, we are always saying, yeah, but we have the monsoon, and that's why there's also days without sun. But actually, the monsoon in India is not everywhere at the same time, right? So on an all-over India perspective, India can really bet on solar. So it's the price of solar itself, but it's also the energy security of solar throughout the year, which makes this country so rich in potential to become the global player in the hydrogen market in the future. And with this, I'll hand over to Mr. Müller-Baum, and then would request Mr. Stefan Halusa to give his closing remarks.
Yeah, first of all, I would like to thank you once again for inviting me. It was really a very interesting webinar here and a very, very interesting discussion. At the beginning, my presentation on our platform itself was very short by purpose in order to have time to discuss more about the content. But if anybody of the participants is interested in our platform, please, as I said, do not hesitate to contact me or my team for further questions. Regarding the potential of hydrogen, not only in India, I think the main sentence is what I've said before: hydrogen becomes the new oil. That's something we are really convinced of. I see a huge potential for hydrogen at international level, and we will see some countries, and India could be one of them, who are the main markets to produce green hydrogen for an international demand, and that's, as I said already, I guess is a big chance for the Indian industry. And having said that, once again, thank you very much for this very interesting discussion.
Mr. Halusa.
Okay, great. Thank you very much, Tobias. Thanks again to all the panelists for your insights and details. I'm not an engineer, so it would be very difficult to me to summarize anything that goes into the technical area. So I would probably go back to some more general statements and probably conclusions from the meeting today. Thanks, Tobias, for sharing this last chart about the solar energy and the potential that India has, because I think that this indeed will play a very important role in the future. I think if you look at on the regulatory side, if you look at what is currently being discussed in Europe under the heading of Green Deal, that will not only have an impact in Europe, but far beyond, because obviously now we will see some carbon border adjustment tax that is going to be defined in one way or the other. So the impact of the Green Deal will go far beyond, and that will reach India as well. And I mean, you said it at the beginning as well. When you look at the potential, I mean, there is obviously the need in Europe to import hydrogen. There is a possibility in India to produce the hydrogen on very competitive pricing. There is a very competitive cost. There is the objective and the target of the Indian government to reach 450 gigawatt of renewable energy production or capacity in the year 2030. That again brings scale, that again brings the cost down, that again opens up the global hydrogen market for India. So there should be a huge impact from that, a huge potential from that. And as Mr. Müller-Baum said at the beginning, it's the new oil. So there is a great opportunity, and we will be very happy to again, as I said in the beginning, to support our member companies to not only fulfill their own objectives and goals in the sustainability arena, but also to benefit from projects being implemented in India and beyond. So I think there was a question in the chat as well towards the funding guidelines. We'll be happy to share them. The Indo-German Energy Forum has them available. We have them available, so please contact us. We can share them with you again. And with that having been said, I would like to thank our partners for organizing this event, the participants, the panelists, and I'm already looking forward to the next one on the transportation, I guess you mentioned, Tobias. So we're already looking forward to that one, so that we, at the end, will cover the complete value chain of hydrogen production and usage. So with that, I would like to conclude, and thanks to everyone again, and have a very pleasant rest of the day, and see you soon.
Thank you.
Thank you very much.
Thank you, everyone.
Thank you very much. Bye.
Bye-bye.
Thank you. Bye-bye.